Okay, so this is basically going to be the first lecture of the school, and the purpose of this lecture is basically to give you an idea of what we want to discuss. And this also serves as a pointer to many of the other lectures that you will see and the tutorials you will see during the school, okay? So it's a very, very light touch introduction to what we're gonna do. You know, some of you may find this too simplistic, okay? Some of you will see these things for the first time. So we have a very broad audience. So, you know, many of you are beginners, many of you are, you know, advanced, electronic structure theorists. So the school is meant to basically serve kind of all kind of backgrounds, right? So we're going to start easy, and then we're going to complicate as we go along during the school. So what we're going to discuss now is the following. First, I would like to introduce a little bit why we care about electron-phonon interactions, and then I'm going to give you a way to think about it in very simple terms, okay, without overcomplicating. And that's going to lead us to basically textbook perturbation theory. Then I'm going to introduce the electron-phonon matrix element, which is the core element for all these calculations, and then explain how challenging it is to calculate that, and why do we need things like one-year functions, okay? And then at the end, I will try to generalize some of this concept to explain what we're going to do during the school. So the next maybe 6 slides are about me trying to convey the message that these things, electron-phonon interactions, are a little bit everywhere. So I'm going to use 3 examples. So this first example is basically a picture of the Green Research Computing ice rack bath in the Texas Advanced Computing Center. It's basically like a bathtub full of oil where you have GPU blades kind of submerged. Okay, what they're doing is trying to experiment a new way of cooling, you know, computers, because they, you know, the heat dissipated by these accelerators is extreme, and it seems that, you know, air cooling is not the most efficient in terms of energy. Now, why I'm putting this in a lecture on electron-phonon interactions? Well, the reason why this heat is being generated is because, you know, when you carry electricity in a transistor, you know, you are basically generating heat, and that heat is generated because of electron-phonon interactions. That means that the electron goes through the solid, you know, it causes vibrations, and these vibrations are heat, okay? And the effect is pretty important if you need that, if you think you need to use oil cooling, you know, in a supercomputing center. So the effect relates to the one of the problems we will study during the school, which is carrier transport. So this is a standard plot that you will find in a very old book about semiconductors. That's semiconductor devices. This is from the 1960s. This is what electrical engineers use in their kind of undergrad training. So if you look at the top curve here, this is the mobility of electrons as a function of temperature on the horizontal axis. In 2 words, the mobility is basically let's say, a velocity of electrons in a solid per unit electric field applied, okay? And what this curve is just showing is that if you increase temperature, this velocity decreases. What is happening is that as you increase temperature, the amplitude of the lattice vibrations increase, and you have more scattering, and the electrons have more difficulty in proceeding, all right? So these scattering processes are leading to generation of heat, and that's why we need to cool electronic devices. So this will be covered by on Wednesday in lectures and tutorials by Samuel Ponce. So the second example, actually, it's to show that this problem that we're going to discuss in this week actually has also pretty big implication in something that seems very far away from it. So this is a model reconstruction, basically it's a plastic model of the ITER, so the International Thermonuclear Experimental Reactor that they're building in Cadarache in France. So the idea is to basically have a plasma inside this donut and then bring it to the point of ignition to generate basically nuclear energy via nuclear fusion. So to keep plasma, which is a charged gas inside this donut, people use a magnetic confinement. That means you need to generate very strong magnetic fields. So the way it is done is to basically wind around this donut here coils this way, and also around the circumference. And these coils use a huge amount of energy because there is a heat dissipation from the electrical resistance. So for this tokamak, for the first time, people will use superconducting cables in order to not dissipate too much electricity. And the cables that we'll be using is basically niobium tin superconductors, which look like this. So the property of these cables is that if you look at the electrical resistance versus temperature, as you cool it down and you go below maybe about 18 Kelvin, the resistance drops exactly 0, okay? So there is no longer any resistance opposed to the transport of electricity. So that's the standard phenomenon of superconductivity. In particular, in this case, is superconductivity mediated or driven by phonons, okay? So that's something that will be discussed in this school, and you will have a lectures on Wednesday also by Roxana Margine about this. Now, a third example, this actually is a picture, a photo from of a field, which is sitting literally 3 miles that way. Okay, it's called the Weberville Solar Farm. It's a small solar farm of 35 megawatts here in Austin, Texas. It serves a small community around the, the edge of the town. And basically, this is just a bunch of silicon solar panels on the ground. And one might wonder, why am I bringing this picture in a discussion of electron-phonon physics? Well, the reason is that basically silicon solar panels do work. Precisely because there is a coupling between electrons and phonons in the silicon semiconductor. To understand that, let me just show you very quickly the most important picture in this field. Basically, this is the absorption coefficient as a function of the photon energy. Okay, this absorption coefficient of silicon basically tells us how many photons silicon can absorb per unit wavelength, right? And just for reference, this rainbow plot is basically the visible light, okay? So it's between 1.5 and let's say 3 point something electron volts. And then below here, there is the infrared range. So sunlight is concentrated between the infrared and basically red. Okay, most of the sun spectrum is in this range. Now, silicon is what is called an indirect gap semiconductor, meaning that the first direct band gap is about here, 3 electron volts, where you see this knee. Now, if the atoms in the silicon lattice were completely fixed in their position, so they were not moving at all, the absorption spectrum of silicon in this range would be exactly 0, okay? Because the photon momentum is very small. So transitions of electrons from valence to conduction must conserve momentum. And in an indirect gap semiconductor, the first transition would light at the direct gap, which is sitting about here in silicon. So the reason why there is this knee here in this plot is that in silicon, there could be transitions that are mediated by phonons, okay? So an electron can make a transition thanks to a photon and a phonon, all right? And this is happening precisely in this range. So this kind of phenomena will be discussed on Wednesday by Manuel Kypakis and on Saturday by Sabyasachi TY. Okay, so now I just want to give you an historical perspective on some of these topics. So this is a paper from 1929, actually. So this is the submission date 28, but the paper was published in 1929. So this gentleman here is Felix Bloch. I'm sure everybody in this room has heard of this name. So this paper actually is famous because in this paper, we basically have the first kind of development of the Bloch theorem, which is probably the most important or the first theorem of solid state physics, right? So for those who don't remember that, if you don't remember your solid state physics, introduction to solid state physics, the theorem basically states that if you have a periodic lattice of many unit cells that look identical to each other, the electron wave function can be written as a product of a plane wave here and a function that is periodic. So it's the same in every unit cell. Okay, that's something that we are familiar with. Now, in the same paper, if you go to the second part, that's a very long paper. It's about 30 pages. Actually, that's an entire PhD thesis of Felix Bloch. In the second part, what it does is to say, well, now that I know how electrons look like in solids, why don't I study how they interact with the lattice? So actually, he discusses what today we call electron-phonon interactions. He called them the interaction between electrons and the elastic waves of the lattice, okay? It's the same concept, but with a different name. And actually, in this paper, he developed the first theory of electrical transport in metals. So this is what was then refined to become the famous Bloch-Gruneisen formula, which is still used today. And it's something one could calculate. And this formula is essentially the basis for understanding electrical transport, these days. Now, these theories are from almost 100 years ago. So one could say that there is not much new, in what we're going to discuss this week. I mean, what is new is basically that most of these things, you see there are some coefficients that are not known. There are many approximations involved. The idea is that these theories provide you with trends, but they're not material specific, and they cannot be used to make quantitative and accurate predictions for different materials. So over the past 100 years, people have done a lot of work in order to improve all of this and try to have something that really has predictive power. In particular, during the past 20 years, with density functional theory and all the associated developments, all of this has become essentially has been transformed into predictive computational tools. All right. So now, what I'm going to do in the next maybe 3-4 slides is to think a little bit about how to, go about electron-phonon interactions to start with. And the first question is that how do they come about? Now, one simple experiment or computer experiment one could do is to take a band structure and see what happens if I move atoms around. So this is a band structure of diamond. So this is the valence bands, just a random kind of semiconductor. And this is what you would do by doing a calculation with any electronic structure code, like this afternoon with quantum espresso, for example. So this is the structure of diamond, this is the valence bands. Now let's imagine that these atoms are vibrating, and they will basically be moving around. So what I could try to do is to see what happens to the band structure if I freeze a vibration into a given snapshot. So the snapshot that you see here is basically a optical mode in diamond. It's basically a vibrational mode where nearest neighbor atoms are vibrating against each other. Okay, a very simple optical mode. So what basically I did here is to freeze this vibration here and then recompute the band structure. And what you see is that there are some changes. Maybe what you notice is that the bottom-most band, basically lowermost band, is unchanged. And then changes start to appear when you go closer to the top of the valence band. For example, here, some bands that were doubly degenerate become now a doublet. Here at the gamma point, there was a triplet, and now they basically split. So clearly, this distortion of the lattice is causing quite some changes in the electronic structure. And if you look at the energy scales, so we're talking about a change of the order of 1 electron volt. So that's a very large change for a displacement that is of the order of 0.01 angstroms, okay? So this is a manifestation of the fact when you move the lattice around, the electrons will respond accordingly, right? And so in principle, one could say, okay, this is the, more or less electron-phonon interactions, I'm done, and we don't need to do the school at this point. Now, this is something that many people do, actually. You just move things around and see how the structure changes. But there are many questions that are left unanswered if you do this. For example, I could ask, how far should I move the atoms here? I use this example, but clearly, if I use a larger distortion, you will see larger splittings here. Okay, so which one do I need to take to compare with an experiment? Maybe one could observe that this is a static snapshot, but in reality, the vibrations are oscillations. So how do I take into account the fact that things are oscillating, and which frequency do I need to use? And the other thing is that these are static band structures. So, I take a crystal, I freeze it, and then look at the band structure. But, if things are oscillating, maybe it could happen that the electrons are actually given some energy or some momentum by the vibrations, and then they will make electronic transitions. So how do I know when these transitions happen and how important these are? And the last thing is that this distortion is, you take a unit cell, you make a distortion, and you repeat the calculation. But, vibrations don't need to be confined in terms of wavelength to the unit cell. They could have a wavelength much larger than the unit cell. In that case, we would need to deal with the phonons finite wave vector. And clearly, this simple approach will not cut it. Okay. So essentially, everything that we're going to discuss in this school is to try to answer some of these questions. So that have to do with how to make this into some kind of predictive tool that I can use to compare with experimental data. So the starting point for pretty much everything we're going to do in practice is density functional theory. Okay, I assume everybody here is familiar with this concept, but if not, there will be plenty of opportunities to catch up during the afternoons. So this is just a schematic representation of the Kohn-Sham equations of density functional theory. You are basically trying to solve some Schrodinger-like equations with an effective potential. If you manage to find the solutions, you can construct the electron density by adding up the square moduli of the wave function in the valence. And then in density functional theory, the potential is a functional of the density. So you plug the density here, that will be the Hartree potential. Here will be the exchange correlation, and then you get this object. Once you have this object, you can bring it back, and you keep looping into a self-consistent cycle. Okay, so that's what the PWACF does in quantum espresso, for example. So this will be covered in detail, in the next lecture and this afternoon by Paolo Giannozzi. Now, the reason I'm putting these slides here is that what you notice is that the atomic positions that would basically be the connecting point with the lattice vibrations only appear here in the interaction potential between the electrons and the lattice. Okay, so these are just Coulomb type interactions, but in a real calculation you would have pseudo potentials. Okay, that's just a complication we're not going to discuss now. But basically, this is where the atoms appear, and that's basically where the electron-Phonon interaction has to come from. So what we can say from this is that after you do the calculation, your wave function, your eigenvalues, your density, and your self-consistent potential, they will all be parametric functions of these positions. Okay, as simple as that. So in other words, we're saying the potential is a parametric function of all of the atomic positions. Now, if you are studying vibrations, you can expect that those will be very small perturbation with respect to the ground state structure. So maybe one can investigate that by performing a Taylor expansion of this potential near the equilibrium. Okay, so clearly these are some limitation, but as a starting point, maybe a good guess. So I take my potential, maybe I displace a single atom just for simplicity, and I can write that the new potential as the original one plus a linear change here plus a quadratic term, and whatever is left, beyond the ground state one is the perturbation Hamiltonian that I need to study to understand electron-Phonon interactions. Okay, so just to put this in visual terms, it's just a cartoon where we have the atoms represented by dots, so red dots. So they generate a self-consistent potential for the electrons that is basically this blue surface. Okay, very simple. And then I imagine moving this, central atom a little bit to the left. So this atom has basically moved from here to here. And my self-consistent potential has changed a little bit. So if I compare this picture with this picture, there's a little bit of a change. So what is the perturbation Hamiltonian? Basically, is the difference between this plot, and there will be something looking like that. So generally, this is a dipole, okay? And this dipole is kind of a complicated object that actually comes from the displacement of the atoms and the fact that the electrons have been screening this charge. Okay, so that's basically the general idea. So what one wants to do to study these problems is to figure out what is the impact of this object on the electronic wave functions and eigenvalues. Okay, so that's pretty much the job. So now to do that, in practice, what we do is that we can use very sophisticated methods we can start discussing tomorrow. But today I'm just gonna give you 3 recipes which are very basic, but they contain a lot of information already. So if I have that change of potential, I can use textbook perturbation theory to figure out the change in the eigenvalues, right? So that means I do take the expectation value of this potential of my unperturbed, let's say, Kohn-Sham wave function, and that gives me the change in energy. From the same recipe of textbook perturbation theory, I can say, well, the change of wave function can be evaluated by taking this matrix element between unperturbed states and my perturbation, divided their energies, and multiplied by the wave function of the unperturbed system. So that allows me to understand how the wave functions are changing. And then I could also imagine that here the displacement is static, but I would like to study a oscillating displacement. In that case, I would need to use the time-dependent, Kohn-Sham equations, and that leads me to time-dependent perturbation theory. So the key recipe in that case is the Fermi golden rule that gives me the transition rate between an initial state to a final state. Okay, and that again given by this matrix m square, and then a Dirac delta function that essentially tells me that the transition will only happen if the energy difference between these two states matches the oscillation frequency of my atomic displacement. Okay. So one could say, why are we discussing this? The answer is that these 3 recipes are the key to understand most of the things we want to do during this week. In particular, so the first recipe is the key to understand how band structures depend on temperature. We're going to see that in a second. Then the second recipe is the key to understand the phonon-assisted optical transition, like absorption or emission, and also to understand how polarons form, how you have self-trapping in a solid. And the third recipe is important to understand, for example, ultra-fast electron dynamics, or also carrier transport like electrical conductivity, electrical mobility, and so on. Okay, so all of these three things are the key to understand all of these phenomena. So what we're going to do now is to go through each of them with each one in one example to just illustrate where we are heading with the school. But before doing that, we need to know what is the displacement in these expressions. So just to go back a second, you see that, for example, in this expression, the change of the potential is the derivative times the change of the atomic position, right? Now, if I double this displacement, clearly this change will double, right? So one has to decide what do I need to place instead of this U in order to compare with an experiment. So there are two options in practice. So one is that I look at equilibrium experiments. So you have a sample held at a given temperature. So that basically means that we study displacements using a statistical kind of thermal ensemble. And the other option is that one studies out of equilibrium systems. For example, you're talking to experimentalists who are doing light-driven system. For example, they pump a laser that excites a specific infrared active mode, and that will oscillate, and the amplitude will depend on the pumping laser. Okay. So the second case is a bit more difficult than what we want to do in this week. So we will focus primarily on basically everything that can be done at a given temperature. So we're going to discuss equilibrium phenomena. Okay. So now, how do we determine the displacement of the atoms at equilibrium? So the idea is that if you have a system of oscillators within the harmonic approximation, which is the easiest thing that we can do, you can prove that that can be mapped into a system of independent harmonic oscillators. Okay, so that means that one has to do the statistical mechanics of simple harmonic oscillators. So that's equivalent to studying basically what is the mean-square displacement of a mass attached to a spring. Okay, physically is exactly the same problem. And to do that, basically we could use, for example, the equipartition theorem, which tells us that the energy of each oscillator has to be proportional to kT, where k is the Boltzmann constant. And that allows us to say that the mean square displacement is basically a line in the temperature. So if you try to plot that, you have the square displacement proportional to temperature. And that's something that you would observe if you do molecular dynamics. If you do classical or ab initio molecular dynamics, you will notice that the mean square displacement will increase linearly with the temperature. Okay. So the thing that one can also do is to be a little bit more accurate and do the quantum statistics of this problem. So basically you study the quantum harmonic oscillator instead of the classical one. And nothing much changes. You just have that this expression is replaced by the Bose-Einstein distribution. And this change of displacement versus temperature follows this blue line. So at high temperature, they're basically the same. At low temperature, the quantum case flattens out. And this is basically what we call the 0-point vibration, okay? So it just means that when you go to zero temperature, the atoms are still vibrating, okay? You have a little bit of 0-point motion, and that's the point where you have a difference between classical and quantum. The only thing one could ask here is that how do I know what is high temperature, what is low temperature? Well, basically that's decided by this characteristic energy here. So if your phonon frequency is much lower than the temperature you're looking at, okay, you're probably in this regime. If your phonon frequency is much higher than your temperature, you're probably in this regime, okay? So it really depends on the materials, how heavy the elements are, and so on. So it's really case by case that one has to decide this. Now, let me tell you about the first recipe, the one to calculate how how bands depend on temperature. And that's basically part of what is known as the Allen-Heine theory. This will be discussed at length during this week. And the idea is basically that I would like to see how the energy eigenvalues change when I have a displacement and an oscillating displacement, and doing the thermal average of this. Now, in the previous two slides, I kind of cheated because I gave you the first order change. But this, if you take the average, it vanishes, because in a harmonic oscillator, you are on the left as many times as you are on the right. Okay, so the average displacement will be 0. So actually, this term, unfortunately, is trivial. It kind of goes to 0. Well, that doesn't mean that there is no energy change. It just means that I need to go to higher order in perturbation theory. So, for example, I need to write down the second order expression for this guy, which is this formula here is, again, textbook perturbation theory. The only thing now that one could notice is that here is the linear change of the potential taken to second order in perturbation theory. But if I look at this expression, I could also imagine taking the the second derivative, the potential, times u squared, okay? And that basically leads to another term that I need to add in order to have a consistent orders in perturbation theory. So these two things are the basis of this Allen-Heine theory. What people do is to pack them together and then to factor out this displacement. Now you have an expression for the change in the energy that is proportional to the square displacement, and then you perform the thermal average. Now this quantity, it's just a coefficient, doesn't depend on temperature. So the only thing that depends on temperature is this guy here. So when you do the thermal average, this becomes an average energy change, and this becomes the Bose-Einstein distribution. All right, so as simple as that. Now, let me show you what happens in practice if you just consider this term, which is the easiest to handle. What is going to happen if you look at the sinus of the denominator? If you look at how this bottom of the conduction band changes, this typically tends to go down if you increase temperature, okay? That's simply because this coefficient is negative. And for the same reason, if you're sitting at the top of the valence band, as you increase temperature, this tends to go up, again, because this coefficient is positive, okay? So the net result in general is that if you look at the band gap will basically tend to decrease with temperature for standard semiconductors, okay? Now I'm saying that standard and in general, I'm saying that because there are some materials for which this trend is reversed, but these are kind of a minority of materials, so I'm not gonna complicate things here. But generally speaking, in simple cases, that's the trend you can expect. Now, what are these two curves? So the red curve would be, let's say, the exact result from this kind of Allen-Heine theory. So the dash curve is what you would get if you were doing DFT and molecular dynamics, okay? So at high temperature, so those two would coincide. When you go to low temperature, basically in DFT, molecular dynamic simulations, at some point at zero temperature, the atoms don't move anymore, right? So you have the static lattice. So you obtain a data point here. So that does not correspond to what is measured in experiment, which actually is sitting down here because you still have quantum zero-point motion in the experiment, okay? So that's something that requires this kind of specialized treatment to capture. So two examples of this type of calculations that actually these are from lectures and tutorials that will take place during the school. So this is basically how the band gap of silicon changes with temperature. And you see this kind of behavior that I described in the previous slide. So triangles are the experiments, and these circles are calculations. So calculations have been performed by Marius Zacharias, who is in the audience, who will give a lecture on the special displacement method that was used to do this. And then on the right, you see actually how the entire band structure, also silicon, changes with temperature. So basically, this is blue is is static lattice, and then red is finite temperature. And this is calculated using a technique called one-year function perturbation theory that will be covered on Saturday by Jemo Lim, who is also in the audience. Okay, so you will basically do plenty of calculations of this type during the school. Let me now show you the second example, which is about change of the wave functions. So why do we care about that? So this is basically what happens to the wave function of a constant state if you distort the lattice. So let's imagine you want to figure out why this is important in optical properties. So here I'm writing the simplest form of the dielectric function of a solid in terms of oscillator strengths. So these are transitions from valence to conduction via the basically the momentum operator, or the standard Fermi-Golden rule with electron-photon interactions. And this Dirac delta basically says that I can make transitions if the change in energy matches the photon energy. Okay. Now, this is the standard calculation that you can do with any simple tools. For example, if you go to Quantum Espresso, there is a little code called epsilon.x will calculate this property for you, and you get basically the epsilon1, epsilon2, real part, imaginary part, and so on, right? So this is for a static lattice. There is no electron-phonon interactions here. So what would be the easiest way to incorporate electron-phonon interactions? So what you can imagine is that as you distort the lattice, the wave functions will change a little bit, and the change will be given by this expression, okay? So let's imagine now replacing this expression inside these two sides of the matrix element. For example, I can say that the conduction will be modified by conduction plus delta conduction. The valence will be modified by valence plus delta valence. So the matrix element is just a little bit more complicated, and I will have terms here that are the product of conduction and valence, conduction and delta valence, delta conduction and valence, and delta conduction, delta valence, okay? It's just a bit more complicated. So just to show you, one of the terms that pop up in this, if you do this, the math, is looking like that. So it's basically the former momentum matrix element, which comes from here. And then the electron-phonon matrix element, which comes from this expansion. And then the denominators here come from these denominators up here. So if you follow this expression, you find valence, momentum, some state, the same state, phonon, conduction. So that should remind you of some plots that you've seen in textbooks where they tell you, oh, there is a way to do indirect optical processes where a phonon helps you go across an indirect bandgap, okay? So the problem is simply the fact that when you have a phonon, it distorts the lattice to break the symmetry, and that allows you a few extra matrix elements to show up in your expressions, okay? That's basically the mechanism by what that happens. And this will be covered in details in the next few days. So just to give you an example from a recent article by Sabyasachi Tiwari. So this is basically the circles are the optical absorption spectrum of silicon, the ones I showed you in the slide about photovoltaics. So the solid line is what you get if you do a calculation using quantum espresso epsilon.x, for example. And as you can see, as I mentioned earlier, you completely miss the important part that allows you to use silicon in a solar cell. Now, if you incorporate this electron-phonon interactions effect, now you get the red line, which recovers the full spectrum, okay? So this is why these kind of things can be important. And this is going to be covered on Wednesday by Emmanuel Kupakis and also on Saturday by Sabyasachi Tiwari. So just as another example, I want to mention a more recent development, which is about not just the absorption, but also the luminescence. In some materials, luminescence needs phonons to happen. So this is the case of germanium. Germanium basically is an infrared detector and can be used as an infrared emitter. And in practice, if you look at the experimental data for photoluminescence, so this is the circles experiment at different temperatures, here, here, and here. If you do a calculation again without taking into account electron-phonon interactions, you get this kind of luminescence spectra here in gray, right? So I guess we can all agree that these are not in a good representation of the experiment. As soon as you incorporate phonons, you have a much better agreement, okay? So this is one case where phonons are not only important for absorption, but also for photoluminescence and to study some of these problems in the infrared. So this will be covered also on Saturday. Now, the third example that I wanted to mention is about time-dependent perturbation theories, the Fermi-Golden rule. So I told you that one can look at the transition rate from a state to another state, right? What I could do with that is the following. Instead of looking at two states, I could ask, what is the transition rate from one state to all other possible states? So what that gives me is basically the transition rate for an electron to go away from a given quantum state, in total, globally. And the inverse of that number is the lifetime of the electron. Basically, is how long the electron spends in that quantum state. So that's basically just a sum of rates. So why that is important? Well, for example, that's important to study carrier transport in semiconductors. So if you look at for example, a conduction band bottom and you have a Fermi level down here, you have a little bit of a population of electrons at the bottom of this band. So what one can do is to calculate these relaxation rates, basically averaged by how the electrons are distributed in this tiny area of the conduction band bottom. From this average lifetime, you can plug this number into an expression for the mobility, which is through the formula, and you can calculate basically how mobility changes with temperature. So that would be the same plot I showed you at the beginning about the mobility of silicon, okay? Now, this expression is extremely simplified. It's just to tell you this in a single slide without going to the details. And on Wednesday, Samuel Ponce will give you much more detail on how to do state-of-the-art calculations of this property. But just to give you two examples, so this is basically, again, the mobility of silicon as a function of temperature. Just look at the top line. So the circles are the experimental data, and the solid line is the calculations, okay? So that's the level of accuracy in good cases, like silicon. And at this point, what one can also do is to see how impurities, contribute to this effect, because semiconductors are not all pure materials. And these are an example of mobility versus the density of defects in the system. And again, circles are experiment, and the lines are the theory. So this will be covered in tutorials by Samuel Ponce on Wednesday, also by Viet and Ha also on Wednesday, okay? So you will see all of these things firsthand. Now, in the remaining few minutes, what I would like to do is to give you a bit more of a heads up of how difficult these things are, okay? Because now we're just looking at the how pretty things are. All of this is pretty easy theory-wise. Calculations seem to be good in comparison experiment. There is a lot of work behind these things, and I just want to tell you what are the main complexities. So this is basically this quantity I've been showing in the previous slides is what we call the electron-phonon matrix element, okay? But this is a kind of a simplified version of it. It's not what we really deal with because things are a little bit more complicated. For one, you remember that I mentioned the block theorem. So all the states we deal with are block waves. So basically we'll have things like electron bands and wave vectors on the left and on the right. So these basically are the periodic parts of the block waves. Then this change of the potential usually is not the displacement of a single atom, is the change of the potential associated with a given phonon. Okay, and to do this calculation, one requires density function perturbation theory, which is a whole monster of a theory and methodology to do these things. And this will be covered by Paolo Giannozzi in the next lecture. So just to show you how complicated this object here in the middle is, I want to give you the full expression. So on the going from right to left, so this is basically the change of the potential, the secondary potential when you move a single atom. This derivative actually needs to be converted into a change associated with a collective phonon displacement. So this is done by multiplying this with the phonon polarization. These are the phonon eigenmodes. Basically, it tells me how each atom is going to move, and then basically by the chain rule, I know what is the total change in this potential. Now, this gives me the direction, but not the distance. So I need to know how far each atom has moved. And this is the 0-point amplitude. This as the dimension of a length. It tells me how far I'm doing that. And then there is a prefactor which makes sure that I transform this object into a lattice periodic function. Okay, so that's why I have this wave vector Q at the bottom. So all of these operations are basically done inside Quantum Espresso, inside EPW and other codes. Okay. Now, why this calculation can be challenging? I want to just use an example that probably is the most representative. Just as an illustration, the calculation of this potential, this one thing here, basically is as expensive as a DFT total energy calculation, roughly. That means that each of these matrix elements is as expensive as a DFT calculation. Now, how many matrix elements do you need to perform a calculation that is reasonable? So this is an example of the relaxation time, so that what is needed for transport calculations, using the golden rule, or the same that I showed you earlier. This time I'm just using all the indices here. And there is some prefactors we don't need to worry about. Square modulus of the matrix element. And then the Dirac delta that tells me that I can scatter only if the energy difference corresponds to plus or minus 1 phonon energy. Now let's just take a simple example. So I take a parabolic band, like a semiconductor conduction band minimum. And I want to know the relaxation time of some carriers that are sitting at this energy. So the intersection of this pink plane with the blue parabola, okay, paraboloid. And for simplicity, let's say that the phonon frequency is negligible, so just 0. So that means that I need to calculate matrix element for all possible states where the Dirac delta here makes sure that the initial state has the same energy as the final state. So if I start, for example, on this corner, I need to do matrix element for all possibilities of going from here to here, then here, 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 here. So basically everywhere around the circle, okay? As simple as that. Now, suppose I do a Brillouin zone sampling in the calculation by specifying a grid. And just to be kind of very coarse, I'm going to say I want to do a 4x4 grid in 2 dimensions. So the main problem that happens is that I need to sample this scattering onto a circle. That's my phase space for scattering. But in a 4x4 grid, the circle gets transformed into a square. Okay. So that means when I try to do the integral, instead of a circle, I'm doing an integral over a square, and that's not going to give me the right number. Okay. So what is the solution here? Well, I need to have enough points that a circle looks like a circle. And basically that means that I need to have many more points in my grid. So there's an example. If you do a 40x40 pixels in your Brillouin zone, you start seeing that your pixelated kind of phase space looks like a circle, and that's fine. So this is just to say that the complexity in this calculation is that very often you need very many matrix elements. And for some of the state-of-the-art calculations, you could go up to 100 by 100 by 100, which means 1 million matrix elements. If you do 1 million DFT calculations, maybe one each is 1 minute, but 1 million minutes is a lot of minutes, okay? So that's the main problem that we are facing. That's for the relaxation time. For many other properties, we have exactly the same problem. It's not quite exactly the same expressions, but it's very similar. So the solutions that we're going to discuss during the school is something that you know, has been worked out during the past maybe 2 decades, and this has been enabled by the development of the one-year function methodologies. Basically, one-year functions are friends or cousins of the block functions. Block functions are extended waves. One-year functions are localized orbitals, like atomic orbitals. And the transformation from one to the other is basically a linear combination that is designed in such a way as to make the properties of the one-year functions as nice as possible. So I'm not going to say much more about this because it's going to be covered extensively today by Nicola Marzari in the third lecture, tomorrow by Antimo Marrazzo in the first lecture, and then by Junfeng Chao on Saturday as well. So you're going to see plenty about one-year functions. I'm not going to spend much time about that. The only reason why I want to, the only thing I want to say is that if you work with one-year functions, there is an inherent advantage in studying electron-phonon matrix elements because you can represent the matrix element instead of block waves using one-year functions. So the picture is the following. You have a one-year function may be sitting here, a one-year function may be sitting here, and then a change of the potential coming from a single atom that sits somewhere else. If those three things are far away from each other, maybe the matrix element will be 0 because they don't overlap, okay? So what that means is that, you know, in this representation, you only need a few matrix elements where these things are close to each other that need to be maintained and calculated in order to proceed with your calculation, okay? So there is a significant saving coming from the use of one-year functions because it kind of takes into account the physics of the localization of this problem. So practically what happens is that this leads to an interpolation formula, which is going to be used in EPW in order to generate many matrix elements starting from just a few matrix elements. That's what we're going to learn throughout this, you know, some of the tutorials tomorrow and Wednesday. Now, just to give you an idea of how localized these things are, this is a plot of matrix element in a one-year function basis by fixing one-year function somewhere and moving the other one away. Basically, the size of the matrix element, you can see, basically decreases, and it decreases in this scale, logarithmic scale. It goes down very, very fast. So that means that as I reach maybe this point, I don't need to evaluate further matrix elements, okay? They're just 0. So I can completely ignore those. And this can be used to reinterpolate back and essentially achieve the same accuracy as what you will get by direct density function perturbation theory calculations, but a much decreased computational cost. So it's just basically a tool for saving time, essentially, okay? But it is quite important because many of the calculations we're going to see during the school without these kind of tools would just take too long, right? Now, these are just an example, another example of one-year functions, you know, just to show you some pretty, you know, one-year functions. These have been calculated by Samuel Ponce and how they decay this matrix element as a function of size. Maybe I will not spend time because you will see much more about this in the next couple of days. And this last slide, I mean, about the technical part, is just to tell you a little bit more about the other topics that I didn't cover in this lecture. So this is the same equation that I showed you earlier for the relaxation rates, okay? And what I told you is that if you have band structures, a matrix element, you can evaluate these quantities. It can be challenging, but it's doable, okay? Now, there is, one could ask, can I do better than this formula? Where could I improve these calculations if my results don't agree with experiments? So one can look at a few bits. For example, this would be Kohn-Sham band structures, DFT band structures. Sometimes your band structures are not good enough, okay? You know that. And there will be lectures and tutorials in the school about how to improve band structures, and this will be based on the many-body GW method, okay? This will be covered by Stephen Louis on Thursday, and then subsequent tutorials. That's for the band structures, but you know, these are also matrix elements that have the wave functions, the self-consistent potential. Sometimes those also are not very good. So you need to do something about that. There are some new developments in this area that will be covered by Zheng Luli on Thursday, which are called GW perturbation theory. So calculating the matrix element at the level of GW theory, essentially, is a recent development that we will cover. Then one could say, okay, again, looking at the band structures, this is all I just said is about electron-electron correlation. So, you know, how to improve, the description of electrons. But I spend a few slides saying that band structures may depend on temperature. So how does temperature enter in the expression? Well, maybe I need to incorporate temperature in these band structures here. How do I do that? Well, this basically will be discussed by Mario Zacharias on Friday and by Jemo Lim on Saturday to science to see how to improve these things by adding temperature dependence in your band structures to be used for actual calculations of other properties. And then maybe one last question one might have is that, you know, why am I giving you this formula? So how do I know that that's okay? You know, one can just write down a Fermi golden rule from textbooks But how do I know that that represents the material property I'm trying to calculate? Well, the answer is basically that this is just a simplification. In order to study what kind of theory one should use, there is a whole formalism, which is a many-body Green's function formalism that one should develop. And this is essentially what you're looking at is an approximation to the formalism. So tomorrow morning, we will cover some of these more advanced things to understand why we use specific formulas for specific quantities, okay? So that's all I wanted to tell you. Just one last slide to say that there are some topics I didn't have the chance to cover. One is about superconductivity, will be covered on Wednesday by Roxana Margine. One is about polarons and electron self-trapping. This will be covered on Thursday by myself, and then there will be tutorials by John Lafuente Bartolome. And then there will be excitons discussed by Stephen Louis on Thursday, and Jen Magdai also on Thursday, okay? So this is basically the last slide. I just wanted to have 3 messages if you forgot everything that I said. That whenever we want to study some of these problems, the starting point should be the easiest possible, and elementary perturbation theory is the right place to start, at least to get an intuitive idea of what's going on. The second thing is that the main challenge in all the calculations we discussed this week is that often you need a very dense sampling of the Brillouin zone, so you need to develop techniques to handle that efficiently. And our take is that the one-year functions are really, the tool that allows us to do that because they are elegant and efficient at the same time. So this is pretty much the end of what I wanted to tell you. And this is a few references that you will find. The lecture is posted on the schedule. So all of the lectures are on the schedule, basically. Some of them are not there yet, but they will be there after the lecture will be given. So all this information is there, and feel free to use it or to ask any questions, okay? So that's basically the end, and thank you for your attention.
And we have now 5-10 minutes for questions from the audience first, and then we'll move on to if there are questions from Zoom. Please go ahead. You want me to speak? Yeah. Yeah, then in the back. Yes, first, and then we'll go in the back. Yeah. So why is the electron-phonon interaction local in the first place?
Local? So it depends on what you mean by local. So in this expression here, so these matrix elements are completely over all the crystal essentially. So there is no locality notion here, but this is just a representation of the electronic structure. So what I tried to mention is that if I do a unitary transformation of block waves into one-year waves, essentially one can rewrite the problem as a problem of one-year functions scattering to each other, essentially, okay? Now, this leads to the notion of locality, but this is actually more of a representation of the problem. It doesn't basically guarantee that things will be local in the following sense. In this plot, for example, in the case of diamond, this matrix element decay as a function of distance between the one-year functions. In other systems, that's not the case, okay? For example, if you take, so diamond is a elemental semiconductor, so it's non-polar. As soon as you take a polar semiconductor like gallium arsenide, so the interactions will be long-ranged, okay? So generally speaking, things can be long-ranged. In that case, this I think will be discussed on Wednesday by Samuel Ponce. What one has to do is to separate the local part and the non-local part. So we deal with the non-local part analytically, exactly, so without one-year functions. And then we deal with the local part using one-year functions. So basically, one breaks the problem in 2 parts. But generally speaking, they can be completely non-local, okay?
So there was somebody in the back here. Yes, please go ahead.
So so that's the point. So that's why we have a wave vectors here, essentially. So when you use wave vectors like K and Q, what we are saying is that we are studying a problem in a much bigger system, which is the Born-von-Karman supercell, meaning that if you have a Brillouin zone grid of 10 by 10 by 10, we are really studying the problem in a periodic box which contains 10 by 10 by 10 unit cells, and your phonon will be commensurate with that one, okay? So the space is increased by the use of basically incommensurate wave vectors. That's the idea. So it can be anything. So you need to speak a bit louder. So yeah, the question is whether we are using a supercell to study matrix element. So the answer is no. So all of these quantities are studied in the unit cell, okay? It's just that by using the block theorem, you can access properties in a larger cell, so the Born-Von-Karman cell, by attaching a wave vector to your wave function in practice, okay? So the Hilbert space is much bigger than the unit cell, but the calculations themselves are performed in the unit cell. That's actually, this is the key kind of advantage of density functional perturbation theory that we'll be discussing in the next lecture. Okay?
Okay. Questions for the audience? If not, we have 2 questions from Zoom.
So maybe first an announcement. So we have almost 300 participants online. Please do not raise the hand because it appears. Maybe you can repeat that.
Okay.
I'm not clear now. So can you hide all the questions in the Q&A? We are answering most of them, and now I will ask 2 live. The first one is in slide 31. What is the difference between G of R0 and G of 0R?
Yeah, okay, so the question is what is the difference between these 2 plots? So these are matrix elements where in this case, one sets one of the wave function, the one-wave functions. So in this plot, let's look at this one. Basically, this is set to the origin, and basically the distance. So this is set as well to the origin, and then this one-wave function is moved away. And then in the second plot, those 2 are sitting in the same unit cell, and the red curve is moved away. Okay, so it's basically, since there are 3 objects, there are 2 plots where I look at the distance. So 2 are sitting in the same unit cell, and the third one is being moved, okay, in 2 different ways. So that's the meaning. Yeah.
Second question: in which case does perturbation theory is not suitable for electron-phonon interaction, and what should we do in that case?
Well, basically, it's perturbation theory is always applies to the case where we have a kind of mild perturbation. So the phonon interaction usually is reasonably small, so that one can apply perturbation theory. So what one can do and what one can verify is whether we need to go to higher orders in the expansion. For example, there are 2 typical cases. The discussion I did was about harmonic phonons. There is a lot of techniques these days to go beyond the harmonic approximation, and that's one, standard improvement. The other thing is that this expansion here, it's quadratic in the displacement, and we could actually go to higher order. So typically, when this is needed, it may be more convenient to use supercell approaches like the ones that will be covered by Mario Zacharias, instead of trying to push to higher orders where the expressions become more and more complicated. Okay.
So final comment, because this has been asked many times. Maybe could you share the website to show where the PDF and the video are?
So okay.